Okay, so thank you for joining, everybody. This is our last webinar of 2025, which is pretty exciting. And today we have Jason Gillham, who's going to talk about our Techno-Economic Model. And Jason is our CTO, COO, and a co-founder of Impossible Metals. Okay, Jason.
Awesome. Thanks, Holly, and thanks everyone for taking some time. Hopefully, everybody has some good holiday plans following this. What I'm keen to do is really talk through our Techno-Economic Model, as Holly mentioned. So this is version 7 of our model, where we've had some change from V6 to V7, and then I'm also looking forward to sharing a little bit about what we have planned for version 8 as part of this presentation as well. So first off, ultimately the Techno-Economic Model is a simulation of our concept of operations. So this animation is our latest animation that really shows what the concept of operations is for our fleet of autonomous vehicles collecting polymetallic nodules. So this will really set the context for what it is that we are simulating from an economic standpoint for the rest of the presentation.
At Impossible Metals, we have developed the Eureka Collection System. Underwater robots are launched from a ship to the ocean floor, where there are vast fields of rocks called polymetallic nodules that are rich in critical metals. Hovering over the ocean floor, the robot uses camera-based artificial intelligence to control its arms, selectively collecting nodules while minimizing sediment disturbance and avoiding all visible life. The collected nodules are stored on board. A large percentage of nodules remain untouched, preserving habitat and biodiversity. Once the robot is full, it ascends to the surface ship. A smart hook autonomously connects to the robot below the wave-affected zone. A crane lifts it aboard using a rail system. The bottom payload door opens, and the nodules are offloaded onto a conveyor belt to transport the nodules to the storage compartments of the ship. The battery is swapped with a fully recharged pack. If required, the vehicle is moved to the maintenance station, where the arm assembly is autonomously swapped out and other maintenance is performed. The full cycle of collecting nodules repeats approximately every 4 hours. Ships travel between the mining area and the processing plant, with full ships departing and empty ships arriving. The swarm of robots remains at sea collecting. Our highly scalable fleet is designed to reach the high production levels required to meet market demand.
So, as I mentioned, the TEA, the Techno-Economic Analysis, is really a simulation of that concept of operations, where we understand some of the operational decisions and design decisions that we make for the vehicle, and then relate those operational design decisions through to a cost and throughput result. Ultimately, from that cost and throughput, we are able to then calculate what is that cost of ton of material from the ocean floor to shore, how much is moving, and what does it cost. So one example of the kind of engineering trade-off and simulation that's taking place in this model is the dynamic buoyancy engine. So when we have more dynamic buoyancy, for example, that means that we will travel faster up and down through the water. That means that we have fewer vehicles and lower cost. But correspondingly, the model also recognizes that by having more buoyancy capacity on the vehicle, that means bigger buoyancy tanks and higher cost, but it doesn't mean only bigger buoyancy tank costs. It also understands that with more and bigger buoyancy tanks, that will need more foam in order to offset that weight. It also means that the vehicle can be taller, meaning more thrusters, more batteries, and all of that is simulated in order to really figure out what is that optimization point, in this case, for understanding how much buoyancy engine should the vehicle have, given all of these interrelationships between the engineering of the vehicle and then the cost of our operations. Last on this slide, I wanted to share a bit of a quote that actually was when I was interviewing a co-op student. They shared it with me, and it really really stuck with me. But it says, "All models are wrong, but some are useful." And I think that that's pretty appropriate for any time that you're looking at any sort of simulation, any sort of model, to say what is. We know that it's going to be wrong. We know that it doesn't perfectly model the reality of what will ultimately transpire. But the important thing is to understand, how do we make decisions based off of this model, and what kinds of confidences can be had based off of what we are seeing. So when in the coming days, probably early next week, on our website, there'll be an updated blog post that will share the latest, the version 7 of the economic model. And when you go into it, you'll end up seeing a spreadsheet that has a number of tabs. And this diagram really shows how information flows through the spreadsheet, ultimately towards helping us make decisions. And so I'm going to walk through this section by section over in the coming bit. So first is our parameters tabs, really broken into 3 areas, one being the site parameters, the technology parameters, and then the market parameters. So for example, site parameters, these are parameters, as the title says, about the site. Things like, what is the depth that we are operating at? What is the, so how deep are we operating? How much current and flow can we expect at that site? And all that fits into the simulation. Similarly, it also talks about nodule sizing, and that's one of the big things that we've really keyed in on with this version 7. It deals with some of the nodule size distributions and our technology's ability to really take advantage of some of that size distribution in order to have superior economics. And so we'll get into that in a bunch of detail through the presentation. The next becomes the technology parameters. So these are parameters about the vehicle itself. Things like, how fast is it traveling? What is the cost for a buoyancy pump, and how does that scale with the flow rates that we require? So as the simulation decides it needs more flow rate from a buoyancy pump, the simulation also understands, because of the technology parameters, how much added cost that comes with. Arm speeds, all sorts of things related to the technology parameters, including some of the costing for all of the sensors that are built into the vehicle itself. The last piece then becomes the market parameters. So these are things like labor rates, fuel rates, things that are really market driven, have some market-based volatility, and we can model those in as well. So all of those parameters then feed into really the modeling portion of the simulation. So this will start with the AUV economic model. This is where we take in the technology parameters, the site parameters, so things like we talked about, how much the buoyancy engine is sized, how big the buoyancy engine is, that sits in the technology parameters. A bigger buoyancy engine means that we have more buoyancy capacity in order to travel faster up and down through the water. And based off site parameters, we're able to know how far we have to travel to ultimately calculate what is that trip time for the AUV, and all of that gets built in through the AUV economic model. Next becomes the maintenance model. This is where we take really 4 main areas of the vehicle: the arms, the buoyancy pumps, the thrusters, and the batteries, and understand how do those get utilized over time, such that we will need to provide rebuilds and repairs of those specific components that we expect to wear over time, and what is the associated costs with that. Lastly, all of that feeding into the fleet economic model that says, okay, this is how many AUVs we need to service, this is how many ships we need, these are the sizes of the AUVs that have pulled through from the technology side parameters. So therefore, this is how large we need the cranes and the ships in order to really pull through what is our annual OPEX, what is the total CAPEX for our operations. Lastly, that pulls through to a summary financials section, which then adds some more overhead based off of the CapEx and the OpEx for back-end operations, and really calculates that total final cost of wet tons to shore. The other interesting piece, we talked a little bit about the buoyancy engine and the trade-off between how a larger buoyancy engine can give us faster travel, but also cost more. So that's one of the two parameters that we optimize through this optimization step. The two really independent variables for our operations that we optimize. One is how big should the buoyancy engines be? That allows us to travel faster up and down. The other is how fast should we be traveling horizontally through the water in order to optimize the overall operation. And so we have this optimization routine that figures out what are the optimal values for those two in order to give us the lowest cost per ton to shore, given all of the vehicle design and site parameters of what we're looking at. Then from that, we're able to do two things. One, we're able to scale because our vehicles are able to incrementally be added into the operations of our overall fleet. We are able to scale very gradually in the eventual P&L for the project. And so the scaling tab understands for one vehicle, for two vehicles, what is the associated CapEx and annual OpEx and production rate, so that when we pull that forward to a project, how does that play into the project? Then the other piece becomes, and this is a key change for version 7, is this top grading sensitivity. So this is the idea that because we have a nodule size distribution and because our vehicles can selectively collect nodules, we are able to program the vehicle to go for larger nodules rather than smaller nodules as we choose, or some distribution thereof, in order to be seeing even better economics than an average distribution. And so that's what the top grading sensitivity gives us, and I'll talk through that in a bunch of detail over the coming slides. So the key changes with version 7, the first is some alignment with TMC's NORAD pre-feasibility study. They've done a great job with really collecting a lot of key data about the region, about the area, and one of the key things in that is further understanding about nodule size distribution. So that's one. The other key thing that we've aligned to is the cost of capital. So they've used an 8% weighted average cost of capital, and so we've aligned to that in our latest economic modeling. And then the nodule size distribution we'll talk about in a second. We've also updated the modeling to be in line with the current vehicle design, as would be expected. But this had to do with some of the conveyor costing. There was some thruster vectoring. Version 6 did not have any thruster vectoring, so that has been added. There were some updates for the arm power. We had some further work with the arms that we're going to be using on these vehicles, understanding the power consumption through experimentation. So that's allowed us to downgrade from a conservative assumption the amount of power that's required. And then there were some updates on the buoyancy engine costing. All of these are not particularly substantial in the scheme of things. With version 7, these have been updated, but aren't overly meaningful in terms of cost implications relative to version 6. The other thing that I want to highlight that, again, isn't highly meaningful from a cost standpoint, but I think is highly meaningful from a confidence standpoint, is that really all of the components for the system are now based off of specific vendor quotes. So we are able to build the actual cost quoted by vendors that we have purchased equipment often for Eureka 2. That's now all built into the model, giving a lot of confidence. We have not considered any volume pricing into any of those costings to date. I do suspect that we will be able to see some substantial cost savings in certain areas of the components for the vehicle, And so that will provide some further benefit down the road. And then the last piece, or I think the second last piece, is that we've removed some remnants of the projected cash flows, project cash flows in the model. When we moved, I think it was around version 5 of the model, we had previous to that been using just a single sheet, a single workbook that incorporated not only the techno-economics, but also incorporated aspects of the project cash flows and a P&L. In version 5, I believe it was, we pulled that out so that there was a separate piece. But in this, in the model version 5 and 6, we had some remnants of that because we were using it for aspects of the optimization. That's now been pulled out, cleaning things up and making it more easily understood what we're doing there. And so that's really, yeah, so previously where we were optimizing for a net present value, we're now optimizing specifically the cost per ton to shore. It worked out to the same in the past, but it's clearer what we're doing now. And then the last piece is modeling the economics with this varying percentage of collection. Because we are selectively collecting with those arms, as you saw in the animation of our concept of operations, we are able to be very selective about how much it is that we are collecting, and we can now see the economic impacts of varying that percentage collection as the key change for version 7. So I want to talk a little bit of top grading in quotes. So much like in a terrestrial mine, where it's possible to choose to leave less valuable ore in the ground and focus just on the more valuable ore, we're doing something similar, or we can model doing something similar, where because we are selectively collecting, and each pick has a relatively constant cost. It doesn't cost us that much more to travel a bit faster through the water horizontally. And so our arms are able to select which nodules they go for. We're able to maintain the mass throughput into the vehicle by targeting larger nodules, traveling slightly faster, and then we're seeing some economic benefits from that. Now, our economics don't require this top grading strategy, but it is interesting, and one of the things we focused on with version 7 is understanding the level of benefit that can be achieved with that strategy because of our technology. So a few slides, and I'm not going to dive into them in a ton of detail, and some of them are harder to read, but I really wanted to highlight and give credit to the TMC NORI PFS, where we're pulling some of this information from. And we had previously been using some published public data that VGR had provided, but it was not as complete and robust as the data that now is public through TMC. The big difference here is the so on this slide you can see the one of the things on this table 6.1, it talks through different types. So TMC has really segmented the box cores that they had collected into 3 different types, type 1, 2, and 3, where type 1 was the majority of the area. I think they specify over 50% of the seabed has this type 1. It's the smaller sizing of nodules. As you get to types 2 and 3, they get to be larger, more spaced nodules. Interestingly, that will have economically, it will be better for us operating in those type 2 and type 3 areas, but the rest of this economic modeling and assessment is all based off of an assumption of collecting in a type 1 area. Next, they provide data related to figure 7.44, showing all, I think, 486, it says, 486 box cores, colored by types 1 as black, 2 as red, or mixed types, 1, 2, 3 is red, and types 2, 3 are shown as green. ultimately, what that then allowed them to do is pull through to say, what is the cumulative probability of the nodules versus the major axis length? So it lets us understand the size distribution of the nodules in the NORI-D area. And then lastly, with all of, because the nodules are slightly pancaked in the CCZ, a lot of their data allows for an understanding of what is that relationship between the major axis of measurement for the nodule relative to the minor axis, in order to come up with a relationship between the volume of the nodules to the major axis of that nodule. So that pulled all of that pulling together allowed us to create this, which says, what is the cumulative percentage of nodules? So as you are sorting the nodules from largest to smallest and picking up a small percentage of nodules, what is the percentage of mass that gets picked up? So as expected, as you get out to 100% of the nodules being picked up, you've picked up 100% of the mass. But the more interesting point is around here, if you can see this point. So down here at about 5% of the nodules picked, we are at about 35%, 30 to 35% of the nodule mass having been able to be collected. And this is what gives us that economic benefit of selecting the larger nodules, because because the number of nodules picked takes about the same cost for us, but we're able to have much less cost for a higher percentage of mass that's been collected. So then this is the result showing that benefit of the top grading that we've simulated and modeled in version 7 of the Techno-Economic Model. So focusing initially on Eureka 3, so that's this solid blue line across the top here. You can see if we are randomly collecting nodules, evenly collecting all sizes from 1 centimeter up to 10 centimeters. The really interesting thing that this has shown us is that down here, collecting about 15% of the material gives us the same economics as collecting all of the material. The really exciting piece for me about this is that what that tells us is that we can go and collect 10% of the material and have the same economics as if we were collecting everything. Because we are collecting all of that material evenly, we can, after years of further study, having collected only 10% of the nodules, come back 10 years later to continue to collect nodules in that area without any change in the economic benefit to us. By having that precautionary approach, that's what's particularly exciting for me with what this has shown. What you can also then see is that with this light blue line, as we're top grading, collecting a fewer percentage, but focused on the larger nodules, we are starting to see about a 40% improvement in the cost. So a reduction of about 40% as we go down to collecting by using a top grading strategy. And then with Eureka 4, which is a larger size system, you can see the same style of behavior where we get a very similar economics, collecting a small percentage in around 15% to if we were collecting 100%. But then you can also see with top grading, we were able to do much better down with this line. The other important note with this is that we show two different extremes. We show an extreme of completely random collection, also an extreme of focused on just the top ones and collecting all of the largest ones. Because of our design and the programmability of our system, we aren't required to operate at one extreme or another. It is possible to operate somewhere in between these. So for Eureka 3, for example, we don't have to operate only at picking up large nodules or only at random. The system could leave a percentage of large nodules, but still be skewed towards larger nodules and operate somewhere in the middle. So for the target operating point, we do certainly see that it is precautionary to collect a smaller percentage of nodules, achieving the same economics in that 5 to 20% of nodules being collected. And then our target operating points at peak economics for Eureka 3, collecting 2.25 million wet tons per year. We're down at about $110 per wet ton of nodule, and Eureka 4 collecting 6.7 or 6.75 million tons per year at $96 per wet ton. So looking ahead to version 8 of the economic model. So in addition to optimizing a specific vehicle for a specific site, which is how we're doing a lot of things right now, version 8 will allow us to take a vehicle that has been optimized for one site and then understand its economic performance at other sites. There will be improved sensitivity analysis within version 8. We currently have some good understanding now about what is most important from an engineering standpoint in order to achieve superior economics, but version 8 will provide a lot of visibility and clarity as to what degree being wrong about one variable versus another will have an impact on our overall economics. With some of that sensitivity and hand in hand with that, it will allow us to give some further probability-based outcomes and certainty of result. So it will allow us to give an understanding of, as we change one of the parameters, say arm speed, for example, if we are right or exceeding what we're expecting by a little bit, how does that impact things? And then the same thing as we see ourselves not achieving those outcomes, how does that impact the economics? And then I think last is that the labor refinement. We haven't looked at some of the labor, build labor, as well as operations labor for a while. And so labor refinement is one of the things that will take place as part of version 8. And so our target release for that, we're looking at April of 26 for then publishing our version 8 of the TEA. And so the final takeaways, the model really is a simulation of our concept of operations. It takes that technical operations and relationships from a physics standpoint, combined with the associated costs of that, to understand, as we change one parameter, how does that ultimately change our cost per ton to shore? It's important to note that our cost per ton to shore incorporates not just OPEX, but CAPEX as well. That's where we are using the weighted average cost of capital of 8% combined with the OPEX in order to understand what is that complete cost for the system. And then top grading, we've talked a bunch about that, where we're able to be selective about what it is that we're picking up. And if we are selective to pick up the largest nodules, that gives us certainly very strong superior economics, but we have very strong economics even while not top grading and collecting a uniform percentage of nodules. So with that, I'm definitely keen for any questions. Holly, why don't I pass it back to you, and you guys, you can help to facilitate as we go.
Sounds great. Excuse me. So if you would raise your hand, the little button's down on the bottom. You'll see the little hand up in the air, and we'll go ahead and call on you in order. So we'll start with Rahul's doing both. Hi, Rahul. Please go ahead and ask your question.
Yeah, okay. Hi, Jason. Can you hear me? Okay. Yeah. Excellent presentation. Very happy to see your assumptions and the way the approach. One comment and one question. The comment is that I'm not sure if you have taken, when you talk about the size of nodules to be picked, whether you have taken the overall grade of the nodule, bulk nodule, because the size of the nodule can vary depending on the size of the nucleus also, which will actually not be something that is useful for you. So this is just a suggestion. Please keep this in mind, that while looking at the size of the nodules, do consider bulk chemistry of the nodule into your economic model. My question is this. I can see that you have considered nodule to shore in the economic model. Are you planning to, or are you already considering the processing cost also in this?
The processing costs. So thank you for the first comment. Really appreciate that. That is not something that is meaningfully incorporated right now, and something that I like the idea of incorporating into the future. So thank you. On this model, the techno-economics looks specifically at the collection cost and the cost of ore to shore. The cost of the processing and the processing strategy gets built into the project P&L modeling, where this feeds into. So if you remember at the start of the presentation, we had the two blue boxes. One was the scaling, the other was the top grading sensitivity. So on the scaling side, that's where we are able to understand, as we scale and increase the number of vehicles, that information moves into the P&L as we scale, and the cost of processing is built into that as well. So that will be not what I presented, but part, as there really isn't meaningful change from V6 to V7, but is part of what is published as part of our overall economic model.
Thank you.
That's great. More questions, anybody? You can also type it in the chat if you would prefer. There we go. Okay, Carrie.
Hold on here. So, Jason, excuse me if I've missed this, but what is the capacity of the collectors? Can you hear me?
Yeah, I can hear you. But I wasn't sure that I understood the question. Do you mind repeating it?
So, what's the carrying capacity of the collectors for nodules?
Yeah, on Eureka 3, it's 4 wet tons of nodules is the carrying capacity for Eureka 3, and it's 12 wet tons for Eureka 4.
Okay, and you said that the trip to the bottom would be calculated to be about 4 hours.
So I don't think I mentioned that. That is roughly what we have been optimizing to from past economic models. I can give it to you specific for version 7. So it's Eureka 3 has a 3.6 hour round trip time. For the overall with the dive to the seabed is about 70.5 minutes is modeled. And then on Eureka 4, it actually is much larger at 5.4 hours, with the dive to the seabed being about 87 minutes.
Okay, and how much time are you calculating for the length of time on the seabed collecting?
Eureka 3 has a collection time of 39 minutes, and Eureka 4 has a collection time of 115.7.
Okay, all right, thank you very much. That's helpful.
All right. Any other questions for Jason today?
Well, if there are no more questions, certainly feel free to reach out to me, to us, either directly if you have my contact, either through LinkedIn or otherwise, or via Holly, or just on our website. There's contact information there. Always happy to engage, answer questions, and help people understand more about what it is that we are doing. But otherwise, I wish everyone a wonderful holiday season, and have a great day.